So, hi everyone. This is Varun from AML department from Savita Engineering College. So, today I'm going to be doing a presentation on QR decompositions using Python. So, let's go into it. Applications in linear algebra and AI. A technical overview for data scientists and AI researchers. So, introduction. The core of matrix factorization. So, QR decomposition is a foundational concepts in linear algebra, essential for solving systems of linear equations and least squares problems. First of all, it factorizes a matrix A into the product of an orthogonal matrix Q and an upper triangular matrix R. So the relationship is expressed as A is equal to QR. The in computational applications, especially in AI and machine learning, this composition enhances numerical stability and efficiency. So, in simple, QR decomposition is a matrix factorization method. Any matrix A can be decomposed into two matrices. So A is equal to Q into R, where Q is referred as orthogonal or orthonormal matrix and R is referred as upper triangular matrix. So here's a question arises: why QR decomposition is crucial? The decomposition method provides distinct computational advantages, making it indispensable for specific tasks in data science and AI. First of all, numerical stability. The orthogonal of Q minimizes the accumulation of rounding errors, offering robust solutions for ill-conditioned systems, critical in large-scale computations. Next comes least squares solutions. It is the preferred method for solving linear least square problems, fundamental to linear regression models in statistics and machine learning. Next, eigenvalues computation. The QR algorithm is the most stable and widely used technique for iteratively calculating the eigenvalues and eigenvectors of the matrix, a core task in PCA. So next comes dimensionality reduction. It plays a role in techniques like principal component analysis, that's PCA, and other matrix approximation methods used to handle high dimensional data. So here are the codes: Python implementation using NumPy for efficiency. We leverage NumPy's highly optimized linear algebra functions to perform QR decomposition quickly and reliably. The matrix A is defined and the linalg.qr function is used to compute the Q and R matrix. So first of all, let's see a code. Like first, we are going to import the library NumPy. Let's import by using the statement import NumPy as np. So we're going to define some data type like Q or decomposition A. So n comma y is equal to a dot space. We're going to define that, and Q is equal to np dot empty, where we're going to specify n and n. So u is equal to np dot empty, where we're going to specify the same, that's n and n. So we are going to define u is equal to u is colon comma 0 and a is colon comma 0 and q with colon comma 0 equal to q u colon comma 0. So for I in range, so for we are going to use a for loop for this. So for I in range 1 comma n, and then we are going to use another for loop that is for j in range, and we are going to declare some elements in it, and r is equal to np dot zeros, and we are going to use another for loop that is for I in range, and we are going to declare n in that, and then we are going to use a for loop that is for j in range. We are going to declare I and n in that. So next here comes a print statement. So we're going to print the Q matrix is, and then we're going to get the input. So next print Q, next print statement, the R matrix is, and we're going to specify we're going to print the R statement. So A is equal to np dot array. So we are going to get the input from the compiler, and we're going to import it. So here comes mutual decomposition process, gram sketched orthogonalization. While libraries handles the computation, understanding the underlying mechanism, often the modified gram sketchment process is key for deep insights. So first point here comes initialize vectors. Start with a column vector of matrix A. Initialize the first column of Q, that is Q1, by normalizing the first column of A, that is A1. Next here comes apply gram sketchment. So iteratively or orthogonalize the remaining column of A against the previously computed orthonormal vectors, that is columns of Q. This removes the components of the new vector that lies in the span of the existing orthonormal set. So next comes normalized columns. That's Q. Normalize each resulting orthogonal vector to create the orthonormal column of the matrix Q. Compute OR matrix. So calculate the elements of the upper triangular matrix R using the inner products between the column of A and the newly formed columns of Q. So typically R is equal to QTA. So we are going to summarize the fact that the power of orthogonality. So first is the core concept. So the core concept of the power of orthogonality is QR decomposition breaks a matrix A into an orthogonal matrix Q and an upper triangular matrix R. Next, a mathematical foundation. It is a fundamental tool rooted deeply in linear algebra, providing structure and simplifying complex matrix operations. So AI relevance, essential for high precision precision tasks in linear regression, eigenvectors computation, that is PCA, and solving linear systems where numerical stability is paramount. So that is all. So finally, we are going to see about the future exploration and resources. Explore the NumPy documentation on linalg.qr. So investigate the role of QR in iterative methods for solving large sparse systems. Study the differences between the classical and modified gram sketchment procedures for stability analysis. Apply QR decomposition to a real-world least square regression problems in a machine learning dataset. So finally, linear algebra is a study of vectors, matrices, and linear transformations. QR decomposition is one of its most elegant and powerful applications. So thank you everyone.